The Western Electric rules for statistical process control tell you when your process is shifting off its center, when it's getting out of control. In this video, we'll go over how those rules do that. So we'll dive into a lot of statistics, but at the end, you'll have a better understanding of how SPC works. Hello, I'm Tom. Welcome to my channel where we talk about continuous improvement in an industrial setting. In this video, it will become a bit more statistical than we usually do because we're going to dive into the Western Electric rules for statistical process control. And all of those 4 rules, they are trying to detect a shift in your production. So that's basically what SPC is designed to do. You have a process, you know that there is a certain natural spread, you take it into account, but you do want to know, is a value that I find so far off the expected mean that there is probably a shift, an actual shift in my process, and should I go and check things out, maybe redirect the process to get it back into its normal state. Now, for that, what it does is we know that there is, from a lot of historical data, a sort of a center line that our process just moves around. But we also know that there is a certain spread, a number of standard deviations of spread. And for those of you who know SPC a little, and if you're watching this specific video, I do hope you know SPC already a little, is that we check 3 standard deviations above or below the center line. And if it goes out of 3, that's already rule 1 of the Western Electric standards, and it means that we immediately have an alert. Now, I'll draw in, let's say, our good process and then a shifted process, and we'll go into the statistical probability of when the rules trigger, but what you're actually looking for as well in both cases. So first, the good process, and then at some point the process goes bad. So basically what you see is that there is some spread around the mean, and at some point it shifts upwards. It doesn't suddenly get a lot more spread, it doesn't suddenly start putting everything on top, but there is a clear transition to a higher average, a higher mean. So if we say that this is, let's say, the length of the widget that we're making, this is still pretty much within the normal ranges. This is also within the normal ranges, but if they're all getting here, the center line has shifted. And okay, my drawing skills were not that good today, but basically we're saying this is the center line here, and the center line has shifted. And this is what we're trying to detect. The Western Electric rules try to detect this effect. That is the signal. When we talk about the signal and the noise, especially within Six Sigma, it is this actual center line is the signal, and what we're getting around it is the noise. So we're trying to make sure that we get back to what is our process doing, and we can only look at so many products to see what the process is doing. And here the noise is still around it, but the signal has shifted. To understand what the basic system is going to do, let's first check what the chances are that this system would have triggered some of our rules. Now, and in this example, I don't actually think I triggered any of the rules, sort of by accident, but we'll take the normal distribution, put it in here as chances. Now for this I will get my notes out because I don't love statistics that much that I know all of these numbers by head, and I do want to give you the correct information. So what this means, these are percentages. If there is a normal distribution and our process behaves itself normally, then 34% of the measured values will be between the center line and 1 sigma, 1 standard deviation higher. And also 34% will be between the center and 1 sigma lower. What that also means is that 68%, these two together, will be between the 2 sigma lines, so between plus and minus 1 standard deviation around the mean. At this point, we should have a look at our rules. And rule 1 basically says 1 point is out of the control limits. So 1 point is over 3 sigma. The chance of getting this is 0.13% if our process has actually not shifted. So in fact, we have a 0.13% chance to be wrong, to give the alarm, operator, your process has shifted, while in practice nothing really bad was happening there. Now this is the easy rule. In fact, rule 4 will again also be the easy rule, but let's go through rule 2 first. So what does rule 2 do? It checks this area. So they are also called area A, B and C. Sometimes you will see that in the literature, but it checks how many points are over 2 sigma. And then you check, are there 2 out of 3 points over 6 sigma? So it's not just 1 point over, because that would be a bit too easy. That's more than 2% of the values, and that is really too much to have as errors in your measurement. But it checks, are 2 out of 3 points over there. And here we'll have to get into a bit of probability statistics. I will allow myself to make some minor, let's say, mistakes, a minor simplification on the system, because some of the scenarios that I will be writing down would not be needed to be put there, so you have to sort of detract them, but this will get you very close to the actual statistical value. So rule 2. 2 out of 3 are higher than 2 sigmas away from the center line. Now, how do we get this? And I'll put it in high or low. One of the situations where you would get this is that all 3 are higher than your sigma norm. But here, of course, the rule would have already triggered on the first 2. Well, the other way indeed to have this. So when you make all the options that you can have that would trigger the rule with 3 samples that you took, if all of them are over 2 sigma, it would trigger the rule. If the first 2 go over and the last didn't, it triggers the rule. First goes over, second doesn't. Third goes over, first is under, second and third are both over. That also triggers the rule. So now we have to work out the probability of these 4 scenarios. And the probability of the first scenario is where we take the top part here. We say, because the up arrow means that it is over here. Now, what is the chance that any one sample from our normal non-error process is over 2 sigmas from the mean? That is this 2.1 plus the 0.13, so this is 2.23%. But this is the 2.3 times 2.3 times 2.3. And that we add up, and this actually is something like 0.001. This is a small percentage. These here have a bit more chance. Why? Because they have 2.3 times 2.3 times almost 1, 97.7%. And this one, they basically have the same. And if you add all of that together, then you get to the total predictive value, actually the total error value of our rule 2, which is about 0.16%. So in 0.13% rule 1 would give a false positive. In 0.16% rule 2 would give a false positive. Rule 3 has the same idea, right? Rule 3 is 4 out of 5 over 1 sigma. So we're looking at this area here. 4 out of 5 over 1 sigma. Oh, this one is still here. And the chance to do that, I will not calculate them all for you, but you get the same idea, which is there are 6 possibilities. They're all over, or the first one or the last one, the middle one is not over. And if you add all of those together, you get to 0.3% chance of having a false positive. And of course, rule 4 is that 8 points are all over the center line. And this one, well, the mathematics looks maybe a bit like this, but there is also another way to think about it. I think this is a good rule to get a bit into the understanding of what we're actually doing with the statistics. If we have a normal distribution around the center line, what is the chance that any point would be higher than the center line? That would be 50%. So what is the chance that 2 points after each other would be higher than the center line? That's 50% times 50%, so that's 25%. So what we do here is we say this 50%, it needs to happen 8 times. So we take 50% to the power of 8. So 50% to the power of 8, 0.4% chance of making an error. These, you see, are very small numbers, although I say small. If you have, and you add this up, it is about 0.5%, because you cannot just add them up, right? If you have if you have values that reach these targets, they also automatically help to reach these rules. So you cannot just add it up, but altogether, roughly 1 in 200 samples will give you a false positive result. Now, in many of the factories I work in, we make about 50 batches a day. That means that you only have 4 days until somewhere there will be an alarm from your SPC chart saying, operator, go check your system, go check if the process is not deviating from the mean. You may have a serious problem. Although we know that this happens when the actual process hasn't really shifted. So that's always what you're a bit fighting with, and that is a reason for many people to leave these 2 rules out and to start with these. Or, funnily enough, to pick the first and the last one, although this one has the biggest chance to get it wrong, and it's also a bit slow. But that is something you have to sort of accept when you do probability statistics. You are never 100% correct. It is all about what chance do I have that I'm making the right choice. And that being said, what we will now look at is what will then happen when a process shifts. So we have the same lines because the control limits, they do not change. We think that this is still the same process and we are interested in this shift. But now if we shifted this process, and I'll put it in here, if this has shifted by 1.5 standard deviations, then it also means that the probability of landing in these zones has also shifted quite a bit. And that is an important part to understand. A 1.5 sigma shifted, but still the same normally distributed process will give you completely different distribution. And this altogether will also again add up to the 0.7. But you see that most of the values will be actually here. 38% is in this sigma line, which is logical because the mean is now here. But that also means that 6.7% of the values that you take, the samples that you take, will be over 3 sigmas in our control chart, because this is only about 1.5 or so sigma. Well, it is 1.5 sigma from the center line. So that is a much more probable thing to reach. In this case, that is a correct triggering of the rule. In fact, this 6.7% means that there is still more than 90% chance that we will not find it, at least not with one measurement. If we take a whole number of measurements, each time you have this almost 7% chance to find it. After a number of times, the chance that you will have found it at least once becomes tremendous. But that means we are a bit slow. We will not find it on, probably we will not find it on the first product that shifted. We probably need a couple more of these things. What now happens, and that's if we take the same idea. So rule 1, it had, I will underline also the percentages for the old ones. Rule 1 had these roughly 0.15, 0.3% chances of being wrong, because, not rule 1, the rules by themselves altogether, because this process did not shift. Now we check how much chance the rules will have when the process did shift. So one measurement over the original 3 sigmas, that's of course that same 6.7%. The second rule with the 2 out of 3 over this line also becomes a lot more probable. In fact, 19% of the distribution of the values where you have a couple of free measurements will be indeed triggering over this rule. For the 4 out of 5 that are over this line, because you need so many basically, it's only 12%, and getting them above the center line, but then we are already testing 8 samples, so we are quite late in detecting this change. It'll give us almost 60% chance to find it. I will also guarantee you that if you have 8 samples, the chance that you triggered rule 1 within those 8 samples is also already almost the same. It's also somewhere around 60%. So this is really what those rules are doing. When your process is behaving normally, there is always a small chance that you still trigger one of the rules, and that is because if we put the rules even stricter, we would not see a pretty big shift in our process, because a 1.5 sigma shift is already quite a serious shift. And you see, there's a small chance that we pick it up immediately, but there's actually also not a very big chance that we pick it up after 3 or 5 samples. So to get a good chance of picking up this shift, this actual shift in our process, we do indeed need, well, somewhere around 8 samples to have a very good power of our analysis to pick it up in at least 80% of the cases. And that's why we do want our operators from time to time to check the process when things are running pretty smoothly, but also you should know that having your process shift like this, and this 1.5 sigma is quite strong. This is the reason why we do not want to have our specification limits at plus and minus 3 standard deviations from the mean. This is in fact what 6 sigma is steering towards. One of the things that we are going for in 6 sigma, where you have even more room, is that even when a process shifts, it will still take you some time before you find out, and in that time we will get in the serious percentage numbers that would have otherwise hit outside of your specifications if you have only 3 sigma instead of 6 sigma. When you get to about 4.5 sigma, this again becomes 0.13. When you get to 6 sigma, it goes to 0.1-ish, in that you will not go over your specifications limits. What this also means is that you should check how often would you like to sample, because if you sample once a day, it will take you somewhere between 5 and 8 days to find a shift in your process. If you sample every hour, it will take you 5 to 8 hours before you find a process. If you sample your product every half minute, it will mean that suddenly these ones will become quite big, and you will have a problem after every 2 hours, roughly, a wrong signal for not really having a problem. So yes, you will detect changes much sooner, but you will also generate quite a lot of false alarms. So that's where you need to balance your SPC, check how expensive is a wrong product or a process shift, and also how close am I to my specification limits. If you really have a, let's say, 4 to 6 sigma process, so a process that is much more capable than the specification limits ask for, then you can relax a bit on the frequency of testing. Don't generate too many false positives, and know that after a couple of hours you will have found the problem. Or maybe, check every 10 minutes, 30 minutes, and it's within a time span of a couple of hours. So a lot of numbers on my flip chart this time. I do hope that it made it more clear how statistical process control works, and then especially not so much how the system works, because you can implement it just believing that the Western Electric rules, they work, and then there's a broader set of rules also to check for some problems that might arise in your sampling. I'll probably make another video about those, although the statistics behind those rules is even more difficult, so I have to think about how to explain that. But like this, you get a feel of what each of those rules is actually doing and what the chance is that it goes wrong, but also what the chances are to detect a shift. And you know now that a very small shift will not be detected. Well, it will be detected at some point, but it will be very difficult. This is already quite a serious shift. When you get to 1.5 to 2.5 sigmas of shift in your process, then you really start detecting it soon, and soon is still somewhere between 5 and 8 samples usually, that it will take you to really get into action mode because you get an alarm to the operator operating the line. Now I hope that you like this a bit more statistical in-depth look at what these rules do and what the error chances are. If you did, don't forget to hit that like button, and also drop me a comment which parts, which pieces of this usually statistical puzzle of Six Sigma would you also like me to explain in such a way, with some examples, some deep dive into how the rules work. Let me know in the comments below. For now, I wish you the best of luck in your Six Sigma journey, and as always, don't forget to also enjoy that improvement journey.